We're going to talk about exceptions to ionization energy trends. And we've learned already, we're going to just talk about the first ionization energy trends. And we've already learned that first ionization energy trends. When we go left to right in the periodic table, the ionization energy, the first ionization energy, tends to increase because we are adding protons, so the effective nuclear charge is increasing. And the key is we're adding protons and electrons. Those electrons are not going into the inner core, so there's no additional shielding happening. Again, that's an oversimplification, but it's what we can use for now. It's acceptable. So, first exception, NS2 to NS2 NP1. When you see these N's, that's your shell number. So this could be any shell number, like 2s2 to 2s2 2p1, or 3s2 to 3s2 3p1. So well, the two examples that you would see on an AP exam are beryllium to boron, magnesium to aluminum. We would expect boron to have a higher first ionization energy than beryllium because of where they are on the periodic table. We would expect aluminum to have a higher first ionization energy than magnesium. But in fact, we find that this is not the case. So here's a problem. Beryllium's first ionization energy is bigger than boron's first ionization energy. Why? So we would expect boron to be bigger. It's not. So to answer this question, first you have to draw the orbital diagrams for these two atoms. And you'll see over here on the left, you must show the orbital diagram. So here we go. Here are the orbital diagrams for beryllium and for boron. Now, when you remove an electron for the first ionization energy, it's always the outermost electron. So in beryllium, we're removing this 2s electron. Boron, we're removing that 2p electron. So you draw this picture. You don't actually have to show the entire orbital diagram. You do have to show the last sublevel showing which electron is being removed. And make a note, for beryllium, a 2s electron is being removed, and for boron, a 2p electron is being removed. It's important to state that. And there are two different explanations. Both of them are acceptable. First explanation. The 2s electrons in boron are slightly shielding the 2p electron that you're removing. So boron's 2p outer electron is easier to remove than beryllium's outer 2s electron. Okay, so what we're saying is, here's our atom, there's the nucleus, and we've got some 2s electrons. They're somewhere in this space, 2s. And we've got a 2p electron that is somewhere in this space. And those 2s electrons are slightly shielding. Those 2s electrons, they're a little bit closer to the nucleus, so they can create some shielding for that 2p electron that's moving around in here. So you're allowed to talk about partial shielding by the 2s electrons, making it easier to remove a 2p electron. Or, this is also another acceptable response to that question. Boron's 2p outer electron has more energy. Remember, a 2p electron has more energy than a 2s electron. So boron's 2p outer electron has more energy than beryllium's outer 2s electron. Therefore, less energy is needed to remove boron's outer 2p electron. So if we look back, orbital diagrams, we can see from this that the 2p is higher energy than a 2s. And since the electron itself has a bit more energy, it takes less energy to actually remove that electron. Okay. Okay, the second exception is NP3 to NP4. Again, N just represents the shell number, so this could be 2p3 to 2p4, or 3p3 to 3p4. The examples of where this exception occurs are nitrogen to oxygen and phosphorus to sulfur. So oxygen is to the right of nitrogen. We would expect oxygen to have a higher first ionization energy, but it doesn't. Turns out oxygen has a lower first ionization energy. Same thing with sulfur. Sulfur has a lower first ionization energy than phosphorus. So here's our problem. Nitrogen's first ionization energy is greater than oxygen's first ionization energy. Why? Now, just like in the last example, you're going to have to draw the orbital diagrams. Again, you don't have to draw the entire orbital diagram. It is okay to just draw the very last sublevel. But the key is you have to show which electron is being removed. So in nitrogen, we're removing a 2p electron. In oxygen, we are also removing a 2p electron. But do you notice something interesting here? Okay. We're going to note that for both nitrogen and oxygen, a 2p outer electron is being removed. But what's going on with the oxygen? Do you notice that these electrons are paired? And if you have a paired set of electrons in one orbital, those electrons will repel each other. And that will make it easier for one of the electrons to leave the atom. Okay. This electron coming off of nitrogen, it's a singleton. It's an unpaired electron. There's nothing pushing it out of the atom, nothing repelling it. So it'll take more energy to pull off that electron, even though oxygen actually has an extra proton. That repulsion, the repelling between the two electrons, makes up for the added proton in oxygen. So here's the full explanation that's accepted. For both nitrogen and oxygen, a 2p outer electron is being removed. In oxygen, the electron comes from an orbital with paired electrons. These repel each other, making the atom require less energy to remove the paired outer 2p electron. Nitrogen's outer 2p electron that is removed is unpaired. That's all you need to say. So we need to talk about it takes less energy to remove an electron if it is in a paired orbital. If the electrons are paired up in a single orbital. Okay. Last new topic for today, ions. So first, we've learned a little bit about ions and their electron configurations in the last video lecture. We know that cations, you take away electrons, anions, you add electrons. We did a couple of electron configurations, but we didn't go over one quick thing. So for the electron configurations of ions, you always take off or add outer shell electrons. This comes into place when we have atoms that fall in the D block. So our example would be zinc 2+. Plus 2 means we're going to take away 2 electrons. Zinc would have been argon 4s2 3d10. We need to take away 2 electrons. We have to take off outer shell electrons, which would be shell 4, not shell 3. So we're going to take away these 2 electrons to get argon in brackets 3d10. Okay, enough on that. Very last topic, sizes of ions. So we're going to be comparing cations to their atoms and anions to their atoms, and then isoelectronic ions to one another. So the first thing, cations. For a cation, positive ion, remember cat, positive ion, you take away electrons, so the ion is smaller than the uncharged atom. Not much to that. You just need to know if you take away electrons, you're getting smaller. What about if we add electrons? Do you think you're going to get bigger or smaller? Hopefully you figured it out. Anions, if you add electrons, the ion is larger than the uncharged atom. Okay, last thing, very last thing. 2 different isoelectronic ions. The ion with more protons is smaller. Okay, so if you're isoelectronic, you have the same number of electrons. An example would be O2 minus and F1 minus. So O2 minus and F1 minus. Those are isoelectronic. They have the same number of electrons. They both have 10 electrons. Now, very important, these do not become neon. They don't become neon. They are isoelectronic to neon. You're defined by your protons, but not your electrons. So these two are isoelectronic with neon, but they are not neon. It's very important. It's a common mistake that students make. They think if you're isoelectronic to another element, then you become the element, but you don't. You don't lose your identity unless you change the number of protons. Okay, so back to, you have two different isoelectronic ions, and the ion with more protons is smaller because this ion will have a larger effective nuclear charge. So you have the same number of electrons, but the one with more protons is smaller because those protons are pulling in the electrons more tightly, making the ion smaller than the other ion. Let's do an example. Which has a larger radius and why? Okay, sodium versus Na1+. That's Na1+. I'm trying to hide the bottom ones. And if you think you know these, just write it down, write your answers, and you can check your answers and stop the recording. Okay, Na versus Na1+. Notice these will both have the same number of protons because they're both Na, 11, 11. But Na1+ has one fewer electron, so this one will be smaller, and the Na will be bigger. And that's what we have. Sodium. These have the same number of protons, but Na+ has one less electron, so Na is larger, or Na1+ is smaller. Okay, Br versus Br1-. So bromine has 35 protons. These both have 35 protons. However, bromine 1-, bromide ion, has an extra electron. That's going to make it bigger. So Br1-. These have the same number of protons, but bromide ion has one more electron than bromine. Therefore, bromide ion is larger. All right, now the isoelectronic example. So sulfur is number 16. Chloride ion is number 17. So sulfur has 16 protons, chloride has 17 protons. These both have 18 electrons. Same number of electrons. However, sulfur has fewer protons, and fewer protons means you pull in the electrons less tightly and you get bigger. So the answer is the sulfide ion. These have the same number of electrons, but S2- has fewer protons than chloride ion. Therefore, sulfide ion is larger in size than the chloride ion. That's it.